Let's take a look at just one more example. This one's a little trickier. We want to find the distance between a point P and a line L. And we have them graphed here for us. So how do we go about doing that? Well, the very first thing we need to understand is what is it asking for? What is the distance between a point and a line? How do we define that? It's not super clear what it should be, right? Because there are lots of ways that I could think about the distance between a point and a line. Right? There are lots of points on the line. To which point am I measuring distance from? To this point over here, or this point here, or this point here? All these will give me different distances, right? So generally, when you're measuring the distance between two objects, and at least one of the objects isn't just a plain point, you take as the distance between them the shortest possible distance. Okay? So we would want something like that. And here's the interesting thing about the distance between this point and the line. The shortest distance will be the orthogonal distance. In other words, we want to go directly to the line. That's going to get us the shortest possible distance, and that's how we define the distance between the point and the line. If we're not orthogonal, if we're not perpendicular, if we take a different route, okay, then we're going to the line, but we're also, we're also going this way a little bit. And that's not what we want. So the shortest possible distance is the direct path. Okay? Okay, great. So, well, it's just the distance between this point and that point, but what the heck is this point? We could kind of eyeball it maybe, but we don't know it exactly. How can we find it exactly? How can we find this distance exactly? So it turns out if we use what we know about vector projections, and if we're clever, we can solve this problem. We could find this distance here, the distance between the point and the line. Okay? So to start with, what we want to do is we want to find a rough guess. Okay? So I'm going to pick some point that I know is on the line. This point here, what is that? That's point -1, -2, -3, -4, 1. I know that's on the line. So I'm going to look at the vector between point P and this point that I know is on the line. Now, obviously, this isn't going to give me what I want, right? This isn't the distance from the line to the point. But what I do get is a triangle. And I can start to use properties of triangles, and in particular, properties of vector projection to get this to work, okay? So point P here, by the way, is, let's see, so that's 1, 2 on the x. And 1, 2 down on the y. So it's the point 2, -2. Which means this vector here, I'll call it vector v. So if I want to end up at P and I want to start at this point, -4, 1, end minus start gets me the vector from -4, 1 to point P. So end minus start, so 2 minus -4 is 6, and -2 minus 1 is -3. Okay, you could also just count, right? 1, 2, 3, 4, 5, 6 to the right, 1, 2, 3 down, 6, -3. Okay. Now what I'm going to do is I'm going to find the vector projection of vector v onto line L. To do that, I need a vector pointing in the same direction as line L. So I'm going to take, again, 2 points that I know are on line L, and I'm going to draw a vector between them. Okay, let's call this vector D. And we could see pretty easily I'm going 2 to the right, I'm going 1 up, right? From here to here. 2 to the right, 1 up. So if I could find the projection of vector V onto vector D, that would be, I'm running out of colors here. That would be this vector right here. So this would be the projection of vector V onto vector D. And what that does is it tells me where the point is that I want to go to, where the point is I want to measure the distance from. Okay, so let's find that. Let's find the projection vector of vector V onto vector D. Okay, so we know the formula. V dot D over vector D dot vector D times vector D. So just plug in. For V dot D, I've written the vectors down here. So vector V dot vector D, that's first component times first component plus second component times second component over, and now D dot D, first component times first component plus second component times second component, and then multiply that by vector D. 2, 1. So in the numerator, 6 times 2 is 12, plus negative 3, that's what, 9? The denominator, 2 times 2 is 4, plus 1 is 5. So I get 9/5 times vector 2, 1. So that gives me 18/5, 9/5. Okay? And so that tells me how far I need to go from this point here to get to the point we're measuring the distance from. Now, I could calculate that vector directly. Okay? I could do it. But perhaps a better way is to find the perpendicular vector. Let's call it V perp. Okay, and this is just vector V minus the projection of V onto D. The length of this vector is the answer I'm looking for. It's the distance. Okay, and I already know all the pieces. I know vector V. I know the projection. I just found it. Okay, so let's do the calculation. V perp is equal to vector V minus the projection of vector V onto vector D. Okay, and just to reiterate, I'm just doing n minus start to find my vector, right? I want my projection vector to end here. I want it to start here. Okay, the vector I want it to end at is the tip of vector V. The vector I want it to start at is the tip of vector, the projection vector. So n minus start gets me what I want. Okay, vector V is, what was it? 6, negative 3. Minus the projection vector, 18/5, 9/5. So if I subtract, just mentally get a common denominator with the fractions. So first component minus first component, that's 6 minus 18/5. If I get a common denominator, that'd be 30/5 minus 18/5, which gives me 12/5. And same thing here, negative 3 minus 9/5. Negative 3 is equal to negative 15 fifths. So negative 15 fifths minus 9 fifths is negative 24 fifths. Okay, so that's the vector pointing directly from the line to the point. That's the shortest possible vector from the line to the point, which means its distance, its length, will give me my answer. It will give me the distance from the line to the point. So my final step, let's take the norm of v perp here. So that's the norm a vector with components 12, 5, negative 24 fifths. I'm going to make this a little simpler on myself, and I'm going to factor out a common scalar multiple. Specifically, I'm going to pull out 12 fifths. Leaves me with the vector 1, negative 2. When I'm taking the norm of a scaled vector like this, I can pull out the absolute value of the scalar from the norm. Because remember, the scalar, it just changes its length and possibly its direction. Since I'm looking for the norm, I don't care about its direction, I just care about the length, which is why we have the absolute value. If it were negative, it would change the direction, and so I need the absolute value, so I'm just focusing on how we're scaling the length. In this case, of course, I don't have a negative, so I don't really need the absolute value. But as a general rule of thumb, if you pull out a scalar from a norm, you need an absolute value. Okay, so absolute value of 12 fifths is just 12 fifths. Square root of the first component squared plus the second component squared. I get 12 fifths times the square root of 5. So that's 12 square roots of 5 over 5, or if you're like me and think about this 5 as square root of 5 squared, you could cancel one of the square roots of 5 on bottom with the square root of 5 on top. And so this would become 12 over root 5. And either of these answers would be acceptable. That is the distance from the line to the point.